So in this example 8.2, we need to reconsider the ideal Rankine cycle that we just did for 8.1. But here we need to consider that the turbine and the pump both have isentropic efficiency of 85%. We just need to determine the thermal efficiency for this new cycle. Okay, so this is the formula for the isentropic efficiency of the turbine. By the way, the formulas are given in the formula sheet. So here, I mean, when we were looking at example 8.1, we were looking at the ideal case. So we already have determined the enthalpy at state 2, but that was for an isentropic case, right? So that's H2S now. So we have the value of isentropic efficiency, all right? We know H1 already, and we in fact know H2S as well. All that we need is H2. So since everything else is known, we can just calculate H2 as H1 minus efficiency, the isentropic efficiency times H1 minus H2S. It is making use of this equation right here. Okay, nothing else. H2S was 1794.8, and when we plug in the numbers, H2 comes out to be 1939. So as I mentioned, H2 is greater than H2S, right? And this is something that you would expect. If H2 comes out to be lower than H2S, then there's a problem in your calculation. So always do a sanity check once you have done some calculation. All right, it should make sense. So for the pump, well, it's sort of a similar scenario. The isentropic efficiency for a pump is the ideal work input by the actual work input, which can also be written in terms of the enthalpies. We already have H4S, okay, but for here, what we could do is we could simply make use of this work input formula. Okay, so we have isentropic efficiency of the pump is equal to the ideal work input, and ideal work input, as we know from before, or a reversible work input, can be written as specific volume times P4 minus P3 and divided by the actual work input. Okay, so we know this value. We know we can calculate the values, or we already know the values for a reversible work input, and from these two we can calculate the actual work input for a pump, and this is simply equal to H4 minus H3. H3 is known, WP is what we calculated just now, so we can get H4 from there. Okay, so this is what we are doing here. We're making use of ideal work input, isentropic efficiency, and calculating the actual work input there. And you plug in the numbers, and this is what it comes out. You can see that the actual work input is 9.48, which is slightly higher than 8 point something we had for the ideal case, right? This part right here. Okay, again here, H4 would be higher than H4S, right? Because this value is simply higher. The difference is not so large, but yes, it's there. And the difference is not so large simply because the work input is pretty small to start off with. All right, so once you have the value, updated value for H4 and H2, we can plug it into this thermal efficiency equation, and this is what we get, 31.4. So we said the thermal efficiency of practical power plants is approaching 45%, but the thermal efficiency that we're having here is 31%. And as you can, and if you notice, it's a huge drop. We had 37.1 in the actual case, but sorry, in the reversible or the ideal case. But when we consider the isentropic efficiencies, it came down to 31%. Okay, so although the isentropic efficiencies here are slightly on the lower end, we have turbines and compressors or turbines and pumps where isentropic efficiencies are sort of reaching 90%, you would say. But certainly, yes, there would be a drop, right? We will not be getting 37% for this case. For an actual case, you would expect somewhere around 31% or slightly higher, and that's not good. Okay, so we have to sort of figure out how we can increase the efficiency.